So yeah, this is a talk called Graph Databases are going to change your freaking life. So the question really is, what are you talking about? What is this thing? What is a graph database? And you might say, oh hey, I've got a dope visualization for you, dog. That's what I'm talking about. This is not correct. It's not what that means. Graph databases are about graph theory and math and stuff, and I'm a web developer for the last, say, about 20 years. I was told there would be no math, that's why I got into this gig. So that's kind of what we're looking at there. So yeah, there's math, but really it's about data. Yeah, what does that mean? It's data. It's about lots and lots of data, and we have lots and lots of, many data that we're dealing with. This is a kind of a cool visualization that was done by a guy named Kim Albrecht, which is actually a visualization of a graph that ties together galaxies in the universe, and it's pretty cool. I just thought it looked neat. And so a lot of times you'll hear graph databases talked about with, say, big business data stuff, and it changes enterprise things and dynamics and words, and ignore all that shit. It doesn't matter. None of that stuff matters. It doesn't mean anything. And zoom in. We all talk about stuff big. We want to zoom in. And we want to think about, how do we represent a thing or an entity or whatever you want to call it, a noun, whatever you want to call that kind of thing. Now, relational databases, most of us have probably used those if you've touched that kind of stuff. If you use anything with SQL, that is typically used with a relational database. Relational databases use a ledger-style structure. That's what they're based on, is ledgers. And a thing is a row in a table. That is how you store a thing. Sometimes you split up a thing into its parts and it's stretched across a few different tables, but generally you have at least some level of entity that is a row in a table. And then what you use are foreign key constraints, and those represent relationships. That just means that in one column in a table, or one column that's in one row in a table, it has this number. Then in another table, there's a column that has a number in a row. And if they're equal, those things are somehow related. It's sort of an agreement that is in the relational database pattern that uses that. And it is a constraint because it says that these two things have to be the same. And like if this is, you can set up a constraint with that foreign key that says, if you put a value into this column over here in this table, and there's not a corresponding value in this table's column over here, then it won't work. It'll say, it will reject that addition. And that's the kind of constraint that you have. Same kind of thing is like, well, if it exists, you may not be able to delete the row that's in here because there's this thing that's attached to it this way. So you set up all these relationships and you set them up with constraints. And that's the key word for relational databases. How do you make relationships between stuff? You make it based on constraints. The table structure is great for things like constraining input and locking things down. It's really, really good at that. If you need something that's really, really rigid, and you need something that is very careful about sort of internally keeping track of that stuff and constraining the things that you can put into it, relational databases do a pretty good job of that. This can get complex and it can get rigid when you're representing relationships, though, and particularly relationships in things that are kind of real world. You might have things like multi-level joins, which are horrible, just terrible things. They're terrible because they are slow and because they're complex. And it's a difficult kind of sort of relationship between how we think about how we think about things in the real world and how we classify them and put them together, and how we might draw things on a whiteboard, and then how we have to translate that into something that fits inside that relational database pattern. We get used to it because that's what most people do, because they store most stuff inside of those relational databases. So we spent lots of time, and there's lots of tools to do that. That's why there's things like object, what do they call this? ORMs, object, right, for mapping, yeah. I didn't do very well in computer science, let me tell you right now. Yeah, well, you have to have that because there is not a very good match between how objects are and represented and how those fit into the relational database. They're not. They have different patterns for storing and structuring things. So, for a second, let's talk about property graphs. Actually, not for a second. We're going to talk a lot about property graphs, so get used to it. Graphs are much, much simpler. They're a lot simpler when you think about them. Those things that you talk about, those entities, whatever you want to call them, you call those nodes, or if you are from the graph theory world, you would call them vertices, but in the graph database world, you often call them nodes. Those are just dots. Nodes have properties on them, and in a property graph model, which is sort of the most common one you see with graph databases, they are usually key value pairs. So, and also, nodes will have labels, and that is how you categorize something. Now, typically in a relational database, you categorize something based on what table it's in. That's how you tell what it is. In this kind of format, you have a label that you apply to a node, and you say, this type of thing is a person, or a user, or a comment, or a blog post, or a tag, or whatever you want it to be. So an example of a node might be something like this. And this is a node, and it has a label, person, and it has 3 properties on it. It has an ID property, which is some kind of unique thing that we use to identify it if we want to. That's numeric, usually you generate that. A lot of systems, there's a plugin for many graph databases or things like that, will automatically generate UUIDs and things like that for those kinds of things. And then we have a couple properties on there, first and last name. So this would be a node which represents not the entirety of me, because I cannot be summed up in this circle, but a first name and last name in there. And then you've got nodes are connected together by something else, and those things are called relationships. They also get called edges if you're looking at graph theory. So vertices and edges in graph theory, but if you're talking about graph databases in particular, we usually call them nodes and relationships. Now, relationships are another type of, I don't know, you might call it an object in a graph. And relationships have a type, typically. That's the type of relationship it is. And they usually have a direction. It varies. Some can be bidirectional, some can only be unidirectional. They have a direction, though, that they face. And they can have properties as well. So if you got a setup with 2 nodes, this is a real simple setup. You got 2 nodes. Both of them are type person. They have that label of person that you've applied to it. So we know that these are person nodes. Those are person entities, or they represent those kinds of entities. And they both have similar properties, but they don't have to. Typically, graph databases don't necessarily enforce schema upon the properties. And then there's a relationship between them, and it's a directional relationship. And that relationship is child of, and it points from the child to the parent. And then there's a property on there of when that relationship was created, which was 2002, when Finkler exploded into the world. So at the end of it, it's just dots and lines. It's dots and lines all the way down from top to bottom. That is what a graph database is. It is dots and it is lines. In a lot of ways, that's simpler, which tends to be appealing. We usually want simpler things. Complex systems break more. So conceptually, it's simpler. It's also more powerful, and it's more powerful specifically when the meaning is in the relationships, when you find a meaning in the relationships between data. So sometimes those are direct relationships, and it'd be like from person A to person B, something like that. And those direct relationships are not particularly hard to do with relational databases. It does not, like the sort of distance between cognitive difficulty and implementation for something like this, and the speed increases that you get with that sort of thing, is not particularly all that amazing. So you can do that in relational databases pretty fine. We have lots of tools for those kinds of things. It's pretty simple to do. Sometimes you have indirect relationships, though. So actor A is related to actor C, but they're related not directly, but indirectly. So how do we find that kind of stuff? And so these kind of indirect relationships, particularly, these things are harder to traverse. That is terrible. These are harder to traverse with relational databases, to jump across these things and find these relationships where there's not a direct connection between the two things. Oftentimes you have to do joins upon joins upon joins. Often the solution for speed's sake is to denormalize and end up having to maintain data in multiple places, and that introduces redundancy, which, yes, it works. Lots of people have done it, but it's complex and hard, and there's a lot of challenges with that. Particularly if you're trying to answer questions that you didn't anticipate when you built the schema in a relational database. And like I said, relational databases are rigid, and I think you realize that when you start working with non-relational databases. They're designed to answer known questions because they're constraint-based, and you have to set up basically it's a big, very rigid rule set. Says it's going to have these many columns, it's going to have these kinds of foreign key constraints, it's going to have constraints on this and this and this. And it works well if your data, the way you're kind of doing it, lends itself to it. When what you're trying to do and the questions you're trying to answer don't lend themselves to that, it's problematic. It can be, they're really designed, like I said, to answer known questions. It can be very hard to answer unknown questions. Questions that were unknown when you built that structure, that schema, and it can be really expensive to refactor things to be performant. So even if you can write a query that could can find, say, indirect relationships between data within the data set, it is probably slow and not performant in other ways too, memory and CPU, all that kind of stuff. So let's say you're the back-end dev or the DB person who handles this kind of stuff and writes these queries that pull data out of a large data set. And somebody, the sales person or somebody who's just trying to do tracking on kinds of stuff says, I want to know how many people have bought a toaster, live in Kansas, and have a criminal record, used the coupon in yesterday's paper to buy that toaster. And you would say, get the hell out. That's not an acceptable question. You should have told me that you wanted to do this when I was making it. Get out. And I think most people who have ever built a database have had that experience. When somebody asks them a question and they're like, F my life. This is going to be horrible because there's no way I can do that. Or if it's just the next several weeks are going to be hellish. And it's because you didn't create a schema that anticipated that question, oftentimes because there's no way to anticipate that question. There's just no way to. There's no way to know the kind of question you're going to ask a year from now or 6 months from now. Sometimes it's 2 weeks from now. You just don't know. You don't know how things are going to change. And the nature is that stuff changes. Now with a graph, you could answer that question. If you have all that data somewhere in there, and there's some kind of paths between those things, you could answer that question. You don't need to know that was the question you're going to answer. So you can say, okay, we know this person, we know what state they live in, we know if they have a criminal record, one way or another. You think they don't know, they totally know. And we have listings of coupons, and we can tie a coupon to a purchase that ties to a credit card that's tied to this person, and this toaster was in that purchase as well, and that person is in Kansas and stuff like that. So you can imagine maybe how those things might be connected together. Each one of those things, like the purchase, the credit card that was used, the state the person lives in, the person itself, if they have a criminal record, the coupon and when the coupon was used and if it was applied to a certain payment or a certain transaction. You have all that data in there, and even if you don't have direct connections between those things, you have indirect connections. And with a graph, it's specifically designed to be able to traverse those kinds of things, because that's what graphs do. And it uses math and stuff that I don't understand, but it works. It's pretty cool. So, and you can add more relationships if you want to. You can say, oh yeah, well, it's kind of a pain. I have to write a kind of a complex query. It might be like 4 lines. 5 lines maybe. What's that? Yes. So you can add more relationships as you want and still be performant. And that's what's really impressive. You can start doing that stuff. The way it's written and the way it's designed is to be able to scan across that whole network of data quickly. So now we get to that egotistical live query time, which it's not too bad because I just pre-wrote all these and it's going to be easy. But if you want to see them, you're either going to need to squint real hard if you're in the back, or I'm going to make this a little bit bigger. So I'm going to Command Tab out of here. Oh, here we go. And go back to this bad boy. So this is a database running on my laptop. It's called Neo4j. It's probably the most common graph database you're going to run into, or the most popular one. Like if you look up graph databases and you're actually like, I'm actually going to use one, Neo4j is going to come up a lot. I think it's pretty accessible. At my company, we offer Neo4j as a service, so that's a thing that we do. Now, up here at the top, please tell me in the back if you can see or not. Yes? All right. Blessed be. We're good. So we've got a list of questions up here. And that's what that query is that I've kind of pre-filled in. And this is a data set of survey data from a nonprofit that I founded called Open Sourcing Mental Illness. If you were here last year, I talked a little bit about it. But this is from the 2016 survey data that we had. And I'm just going to show you how you kind of extract some different kinds of data out of that kind of stuff using graph queries. And Neo4j supports this query language called Cypher. And it kind of looks like ASCII art to represent relationships. There are other ways and other languages that are used to traverse databases. A common one is called Gremlin, which is a DSL written in Groovy. That is probably the second most common one that you'll see. And it's very different. It looks like you have a fluent interface with like, do this dot, do this dot, do this dot, do this. So it's much more sort of like an object-oriented fluent kind of deal. This is more like SQL. So to some extent, you can probably kind of figure out what's going on here. It's going to do a match, which is a lot like kind of like a select in SQL. And it's going to do a match of nodes of the type question that have the label question. And it's going to assign in each one of the things, the results that comes back, it's going to assign that to the letter Q. That's kind of a placeholder or a variable name. So, and then I'm going to return Q, and I'm going to order it by a property that's on Q called order. So then I'm going to go ahead and just hit play on that bad boy. And this shows me Neo4j's stuff is smart enough where it can also see relationships between the data that you've returned. And this is actually a network of all the questions that are in there and how they're linked together. And if I click on one, you can drag it around and stuff and do this kind of junk, which is, it's fun for like a couple seconds. And, but if you want to look at like what it's kind of returning, this is really the meat of it, and this is kind of hard to see, so I'm going to make that a little bit bigger. Hopefully you can kind of see. It's going to do a bunch of rows here. I'm going to close this guy. It's going to return me a bunch of rows here. And each one of these is a map that represents the entire node that got returned and all the properties on it. So this is one node. Question is, the field ID is this, question ID is this, how many responses we got back, what the idea was, what the UU idea was, which is auto-assigned by a plugin with Neo4j. The order is 0. If we look at the text, that is completely unreadable, so I'm not going to look at that. And then if we look at the code, you can kind of see that stuff down here. This is what actually comes back over the transport. There are two ways in Neo4j. It uses a REST API, or in the newer 3.0 versions, it uses also a binary protocol called Bolt. Either one, this is the actual data structure you get back, which is just JSON. And then you would use some kind of client to read that stuff out. So anyway, that's a simple query in there. So let's look at some other queries, though. And here's a simple one. This just returns a single question, and it matches a property. That property is field ID. And this is a particular one that I happen to know. It's going to be, have you ever sought treatment for a mental health issue from a mental health professional? So I'm going to go ahead and hit that. And there's one node, it only returns one node because that's all we've got. And it returns the properties of it. That's okay, that's interesting. And then let's see something else. All right, one more. We're gonna match that same question, and then this is where relationship stuff comes in. This is the query from beginning, here's the tail of it, here's the head of it. That's the relationship we're going to look for, a direct relationship of type has answer that is pointed in this direction towards a node that is labeled answer, and we're going to assign that to A, and then we're going to return Q and A. So this is a one question and all the answers associated with it. There's two answers associated with it because it's a yes or no question. And so when we look at the data that gets returned, in each row, it sort of builds out the same question node, and then there's two different answer nodes. All right, that's all very exciting and things like that. Now let's take a look at something that gets a little more interesting. We match that same question. We have that same answer. But then we have another part of this path that says, I want to tie a person who has answered that question with that answer back to that here. And this is going to give us the first 200 people who've answered that because there's going to be about 1,500. I didn't want to get all of those back. But this is basically going to give me everybody who's answered this question, and it's going to break it out by answer. So we have answer one, answer one, answer one, and it's breaking out. It actually just shows the people, because I look now looking at this, I think I told you the wrong thing. I'm just returning the A and the P, so the answer and the person in each row. And so that's going to return what was the answer that the person gave, and then who was that person. And what we know is like where it was the referrer, what was their user agent, stuff like that, because it was an anonymous survey. As anonymous as you can be on the internet. Okay, so that's all very interesting. But let's look at something a little more complex. Match question, has answer, answered, person, person, lives in country C. And let's do something even, that's not surprising, and a relatively easy one to answer. This just gives us rows, and I can't see anything on that. Let me see here. I don't know if there's something, I think it might be a bug with the, I wonder if that's a bug with that guy. Let's see here. Let me see if I can change the dark to light. Hey, I can see that a little bit better. Here we can see it's pressing this stuff out so that we're not returning nodes, and so it doesn't, because we're not returning nodes or these kind of objects, we don't get a graph representation of visualization automatically with it. But we get the properties back here. Q question, A answer, C name, the name of the country, and how many people from that country answered with that. So one person in Afghanistan said 0 or no. One person said yes. Australia, 11 people said no, 24 people said yes. So it breaks it out based on country. So that's kind of interesting, maybe. Here's a thing, which is, let me make that a little bigger, and we can see this. And I know it doesn't use the syntax highlighting anymore, but you still hopefully can kind of see fairly well how it goes. This is going to give us percentages of the current diagnoses, and it shows us doing a couple different things here. I just want a count of all the people. So I match P person, and then with count P as person's total, I pass that value in then to the next match, which is the thing that you can do with Cypher to sort of filter down through steps. And in this case then, what I'm doing is, then I'm getting a count of all the people who have a current diagnosis. And so my next step is I get a count of that, count RCD, which is actually counting the number of relationships and what comes back. And then I pass both of those back, diagnosed total, person's total. Then the third match is really what's interesting, where I'm matching person who has a relationship to called current diagnosis to a disorder with count P as count D is like the name of the diagnosis, then the diagnosed total and the person's total, and then I return all this stuff. And here, when I'm doing stuff here, what I'm doing is I'm calculating it as percentages as opposed to just raw numbers. You of course could do that on the application side, but that's kind of what you're looking at. So let's run that, and that gives us these numbers here. And it does that pretty quickly, I think, which is sort of interesting. You can see some counts on here, 133 milliseconds. Now, that's all very fine and dandy and real interesting, but here's a more complex thing, and I think it'll show you how powerful some of these things can get. This is the incidence of self-diagnoses without a corresponding diagnosis by a medical professional, compared to whether or not that person's employer has provided mental health coverage. So how can I answer that question? If you were looking at this in a relational database, there's going to be a number of joins that are probably happening. Question to answer, and then if answered, self-diagnosis and professional diagnosis all represent pivot tables. Then you're probably looking at a question to answer, person to answer, person to person self-diagnosis, diagnosis, person to professional diagnosis, and diagnosis relationship would also likely be a pivot table. I'm not good with that stuff, but I help a friend of mine who was much smarter at those things help me write that. But we did write this out. I'm going to pull the profile out because that's not something we need. That is a way to actually sort of like see how things perform and what was happening. But the first thing we do is we get the totals so that we can calculate percentages. And that's kind of like how we did that before. And so we take this where we match a question to a particular field ID. So because we're interested in a particular question, we're not returning an answer, but we're going to get an answer here. We have it's connected to a person, and then it has that relationship self-diagnosis and had diagnosis D. You can kind of trace through this thing and see all of the different levels of path that you have to go through here. So we get those numbers, and we get also the questions, all the questions and all the disorders. And if we get those out, we query them just once, then we don't have to query them again later. So now we do a query to get the counts from each answer for self-diagnoses. So this is the stuff that gets kind of interesting. So we say that same question has answer of A, so then we're going to assign each of those answers to A, answered by a person P who had a self-diagnosis D, where they don't have a professional diagnosis, where there's not a match between a relationship of a person to a professional diagnosis, which would probably be a disorder node that was sitting someplace else. So they don't have a match like that. And then we return the question, the diagnosis, the answer, and the percentage of people who matched above with that answer. So I return question, name, answer, question, disorder name, answer text, the percentage of total as percent, and then order by this. So let's go ahead and run that. So that is, if you line that up, depends on how I formatted it, that's 5 lines of code. It wraps a little bit. But this gives us a breakdown then of, okay, here's the question. It's the same question every time. Here's the disorder they have. This is the answer that they gave, that if they have that disorder. And this is the percentage of people who have that disorder who answered that question like that. So 33% of people with an addictive disorder who I said that their employer, to the question, their employer provides mental health care coverage, says, I don't know. And these are people who self-diagnose with an addictive disorder. These are not people and they do not have a medical diagnosis at all. And so we break those down, anxiety disorders, Asperger's, and things like that. So we break all that stuff down, and we can get percentages out of that stuff, which I think is pretty interesting, and you can do it fairly succinctly with only a couple diagnoses, which is kind of cool. So that gives you an example of sort of how you can do that. And let's pop back into there, but I think you can kind of, hopefully you've gotten a feel for how that works out for you. So the one thing I'd say about this kind of stuff is that it is powerful, and you can do lots of different stuff. You can find indirect relationships. You can find lots of questions you maybe didn't anticipate answers for. And I think that's really, really cool. But it's not magic. It doesn't solve everything for you. You can write queries that are incredibly non-performant and don't do anything for 10 minutes. And you can do stuff that breaks things. And that totally happens. And that's certainly, just like every other tool, there's stuff about it that sucks. So they're not magic, and they don't solve all your problems. There's some things that relational databases do better. There's some things that document databases do better, things like that. But particularly if you're asking questions about data, and it's really about the relationships between data, or it involves the relationships between data, they're really powerful and really nice, and sometimes it seems like witchcraft, especially if you have a lot of data, which is very, very bueno to me. So, there's some links that you can check out. Data is for fun and exploration. You can check out graphstory.com. It's the company I'm CTO at. There is, so if you don't want to bring it up yourself, you can bring it up with our trial. And you can ask me questions. If you type into the little web chat thing, I or the CEO answers those questions, not somebody else. There's some good example data at neo4j.com. And then if you're interested in that survey data and helping us develop an API for that and doing queries against that kind of stuff at OSMI, Open Sourcing Mental Illness, you can check it out on GitHub. That project is all open source and up there. So that's what I got for you today, question time. And if you got any questions, feel free to ask.